The third form of nonlinearity we are looking at would be polynomials. Remember that a polynomial of degree n would just be x to the power of n, right? So now we can look at an example, and that would be the quadratic model. So, for example, if you want to explain the variation in test score by using income. So you have the intercept, you have the slope, which is the effect 1 unit of income has on the test score. What if we believe that test score and income has a more quadratic relationship, which either is like upward sloping or it's convex or concave? Then we would use the quadratic regression model, and it's quadratic because we have this income to the power of 2. So now test score, it's dependent on the intercept, it's dependent on the linear slope, the income, and it's dependent on the income squared, okay, the quadratic term. So to make this quadratic variable, you would just make a new variable, and the value in this new variable would just be the value of income to the power of 2. So income times income would be the value in this income squared variable. And now we can test the hypothesis that the model is linear versus quadratic by testing the null hypothesis of beta 2, the slope on the quadratic term, by a t-test. Okay, so what about higher order polynomials? We can easily make a model or define a model which has a polynomial to the power m, right? And what you have to think about is that if you include these higher order terms, then you should have a very good reason to do so. For example, some models they include the temperature to the power of 3 to explain the power prices, the electricity prices. So interpretation is actually quite straightforward. Suppose we have the quadratic formula, and to take the derivative of y with respect to x, we see that the effect of the change here in x on y depends on the value of x. So you have a small change in y. This is a change in y relative to a change in x, and this is equal to the linear slope times the 2 times the quadratic slope, the slope for the quadratic term, times the x itself, right? So to go to our example with the test score on income and income squared, then the effect of an increase in income on test scores is greater or is different than if you go from 10,000 to 11,000 than from 30,000 to 31,000. you might hypothesize that the relationship is upwards sloping but concave, right? So an increase of $1,000 is more important for the test scores of a poor family than it's for a rich family, right? So how do you know how many terms to include in the polynomial model? So which degree polynomial should you use? Well, one approach is to use a sequential hypothesis test to see whether or not the highest degree polynomial can be omitted from the equation. If the beta is different from 0, statistically speaking, then you include it in the model. Okay, but a word of caution: if you have a lot of data, then even small differences might be statistically significant, but not economically significant. Okay, so if you have a lot of data, then you might end up with a very large model which is fitting your existing data very well, but it's not useful for explaining any unseen data. So it's not very good for prediction or forecasting. But this is a very, with that in mind, with that caution in mind, we can show you a very simple algorithm to decide whether or not to include the term in the model. So first of all, you can pick a maximum value of m. Okay, so this would be the x to the power of m, right? You make that variable, and you make all the variables with powers less than m, right? And include them in the model. So you pick a maximum value of m and estimate the polynomial regression for that m, right? Then you use the t-statistic to test the hypothesis that the coefficient on xm, the beta is 0. Okay, so the null hypothesis is that of beta m equal to 0. The alternative hypothesis is that the beta m differs from 0, right? So if you do not reject the beta, then you just eliminate that variable in your regression, and you rerun the regression. Then now the highest polynomial is x to the power of m minus 1, right? So, and you just perform the same tests on this coefficient, the beta m minus 1, right? So the test you perform is the t-test. So you just use the critical t-value and check versus the t-stat. Okay. If you do not reject the beta, then well, let's see, yeah, if you reject the test, you use that polynomial and those polynomials with lesser degree in your model. Okay, you keep them. And if you do not reject the beta different from beta equal to 0, then you just take the highest polynomial out and rerun the regression until you have a beta which is statistically significantly different from 0. And then you're done. You have a model which, based on the statistics, is the correct model to use. So there is one missing ingredient, and that is, how do you pick m to begin with? Okay, how do you pick the initial degree of the polynomial? Well, according to economic data, then you would not pick a degree of m which is very high. Most of the times you would not pick any term with m more than 2. But in some cases you would pick even 3 or 4 in step 1 and just check it versus your data. So yeah, that's the next video. So see you next time.